So moving into the next question, which is question number 16. The ABCD parameters of a three-phase overhead transmission line are A is equal to D is equal to 0.9 angle 0, 0. B is equal to 200 angle 90 degree. C is equal to 0.95 into 10 raised to minus 3 angle 90 degree S. At no load condition, a shunt inductive reactor is connected at the receiving end of the line to limit the receiving end voltage to be equal to the sending end voltage. So the ohmic value of the reactor is to be found out. So we are going to connect a shunt inductor. We have discussed connecting shunt inductor at the end of the receiving end of the transmission line when we discussed the theory topic with respect to Ferranti effect. So you have to directly go to the theory portion and study the conditions of Ferranti effect and the effect of connecting a shunt inductor at the receiving end of the transmission line. And the value, how to find out the ohmic value of the reactor. So all these equations are directly given with respect to the theory. And here you can see the value of the shunt inductor. If it is not given in terms of ABCD parameters in the theory, you can just write down this expression. The XL value of the shunt inductor is equal to B divided by 1 minus A. So B is directly given, A is also given. So B divided by 1 minus A can be substituted, which will give you 2000 angle 90 degree. So what is our answer? Our answer is equal to 2000 ohm. So the value of the reactance of the shunt inductor is equal to B divided by 1 minus A. Moving into the next question, question number 17. A surge of 20 kV magnitude travels along a lossless cable towards its junction with two identical lossless overhead transmission lines. So it is the case of a T junction. The inductance and capacitance of the cable are given as 0.4 millihenry and 0.5 microfarad. The inductance and capacitance of the overhead transmission line are 1.5 millihenry and 0.15 microfarad per kilometer. The magnitude of the voltage at the junction due to the surge is what is the question. So directly we are given with all the values, and here ZC is the surge impedance of the cable and Z1 and Z2 are the impedances of the overhead line. So it is directly given because Z1 is equal to Z2 and ZC is also given. So here we can see Z1 is equal to Z2. So first we are going to find out the parameters of the cable. The inductance is given, capacitance is given. So we can find out the surge impedance of the cable. So it is root of L divided by C. So surge impedance of the cable is obtained as 28.28. Now we can find out the parameters of the overhead line. The inductance and capacitance of the transmission line are given. The surge impedance of the line can be found out by root of L divided by C. So it comes to be 316.22. So what is the magnitude of the voltage that is impinging? A surge of 20 kV magnitude is impinging into the junction. So the surge value is equal to 20 kV. And what is the junction voltage equation? It is 2E plus 2E into 1 by ZC divided by, so this expression is directly given in the theory topic dealing with the reflection and refraction of waves at various ends of a transmission overhead line. Okay, so it is 2E into 1 by ZC divided by whole divided by 1 by ZC plus 1 by Z1 plus 1 by Z2. All values are known. When you are substituting, you will get the value to be 33.93. So what is our answer? Our answer is option D, which is 33.93 kV. So that is answer for question number 17. So these are good questions. A question of this form can come for your exam also. Sometimes they will be giving another value of Z2. So you will have to find out the surge impedance of line 1, which is Z1, and line 2, which is Z2, and then Z1 will not be equal to Z2. So this is question number 17. Now moving into question number 18. The generalized circuit constants of a three-phase 220 kV rated voltage medium length transmission line are. So A is equal to D is given, B is given, C is also given. If the load at the receiving end is 50 megawatt at 220 kV with a power factor of 0.9 lagging, then magnitude of line to line sending end voltage. So we will have to find out the value of V of S line to line sending end voltage. Okay, so the generalized constant of a 220 kV rated voltage line, medium length transmission line is given. So A is given, B is given, okay, and we will have to calculate the value of IR. So what is the value of the line current? Voltage is given and the net power is given as 50 megawatt. So 50 megawatt divided by root 3 into 220 kV into the power factor 0.9 lagging will give you the value of the current IR. So we have obtained the value of the current IR. And what is expression for the sending end voltage? Sending end voltage V of S is equal to A VR plus B IR. Okay, so you have to remember all these things, my dear guys. Okay, else you will not be able to do this kind of a problem. But if you have completely studied all the theory portions that I have taught you, and you have completely doing all the practice questions and also all the previous questions, you are going to be damn good in power systems. Okay, and this is going to fetch you a great future. Not only for any exams like GATE or the ESE, but for any other examinations. If you don't know power system and machines very well, you are going to suffer all through your career. Okay, so what is VFS? VFS is equal to A VR into B IR. We have found out IR, A is given, B is given. Substitute all these values into this. So you will be getting the phase voltage as 133.23 angle 7.77, and then you will have to find out the line voltage. So to find the line voltage, you will be multiplying it with the root 3 and your line voltage will be obtained as 230.78. So what is our answer? Our answer is option C, which is 230.78 kV. So that is about question number 18. Moving into question number 19. The parameters of a transposed overhead transmission line are given as the self-reactance XS is equal to 0.4 ohm per kilometer and mutual reactance XM equal to 0.1 ohm per kilometer. Now the positive sequence reactance X1 and zero sequence reactance X0 respectively in ohm per kilometer are is what is the question. So you have to find out the positive sequence reactance X1 and zero sequence reactance X0. So self-reactance XS is given and mutual reactance XM is given. So for the transmission line, we know the positive sequence impedance. What is positive sequence impedance? X1 is equal to XS minus XM, and X0, which is the zero sequence impedance, is equal to XS plus 2XM. Very important. So write down these expressions. Our X1 positive sequence impedance is equal to XS minus XM, and zero sequence reactance is equal to XS plus 2XM. So XS and XM are given. You will be able to substitute and get the values of 0.3 and 0.6, which is option D for question number 19. Now moving into the next question, question number 20. The concept of an electrically short, medium and long line is primarily based on nominal voltage of the line, physical length of the line, wavelength of the line, power transmitted over the line. So what is our conclusion? Our conclusion is that if L is the length of the line and it is greater than 80 kilometers, we say it is short line. 80 to 240 or 80 to 250 kilometers, we say it is a medium line. Greater than 250 kilometers, we say it is a long line. So it is less than 80, and from 80 to 250, and then it is greater than 250. So it is less than 80, 80 to 250 and greater than 250. So what is our condition of classifying a line into short, medium and long transmission line? It is purely based on the physical length of the line. So that is about question number 20. Moving into the next question, question number 21. ABCD constants of a 220 kV line are A is equal to D is equal to 0.94 angle 10, B is equal to 130 angle 730 degree, and C is equal to 0.001 angle 900 degree. If the sending end voltage of a line for a given load delivered at a nominal voltage 240 kV, then the percentage voltage regulation of the line is to be found out. So we will have to know the sending end voltage and the receiving end voltage to find out the voltage regulation of the line. So the sending end voltage is obtained as 240. Now the full load receiving end voltage is equal to 220. So what is the sending end voltage per phase? It is 240 divided by root 3 kV. Now what is VFS? VFS is equal to A VR plus B IR at no load condition, because we are going to find out the voltage of the line for a given load delivered at a nominal voltage is 240 kV. The percentage voltage regulation of the line. So we will have to find out, this is the loaded voltage of the line as 240 kV. We will have to find out the no load condition voltage of the line. So we will have to go for IR is equal to 0. So the second term will be equal to 0. So VFS is equal to A VR. So the no load receiving end voltage is equal to VFS A VR. So that means what is V of R? V of R is equal to VFS divided by A. So it is VFS divided by A. What is the normal VFS? Normal VFS is equal to 240 kV. So it is normal 240 divided by root 3 into A. What is A? A is equal to 0.94. So substituting the value of A, we will be getting the no load receiving end voltage as 255.32 divided by root 3. So we will have to find out the voltage regulation of the system. So then what is the no load receiving end voltage of the line to line voltage of the line? So it is equal to 255.32, because the root 3 will not be there. So it is 255.32. And then what is the normal receiving end voltage of the line at full load? It is 220 kV. So what is voltage regulation of the line? It is the no load voltage minus full load voltage divided by full load into 100%. So what is our no load voltage? It is 255.32. So when the line is fully loaded, our voltage reduces to 220 kV. But when the line becomes no loaded, the voltage rises to 255.32. So a line which is at no load has a terminal voltage of 255.32, and when it is fully loaded, the voltage dips to 220 kV. So you can see the value, the actual difference of voltage that happens on a transmission line when the line is subjected to the no load condition, which is the increased voltage, and when the line is subjected to the full load condition, which is the maximum reduced voltage. So what is our voltage regulation? It is the receiving end no load voltage minus receiving end full load voltage divided by receiving end full load voltage into 100%. So it is 255.32 minus 220 divided by 220 into 100%, which will give you 16% voltage regulation. So what is our answer? Our answer is option C for question number 21. Now moving into the next question, question number 22. A single phase transmission line and a telephone line are both symmetrically strung one below the other in horizontal configuration on a common tower. The shortest and the longest distances between the phase and the telephone conductors are 2.5 meters and 3 meters respectively. The voltage induced in the telephone circuit due to 50 Hertz current of 100 amperes in the power circuit. So we are going to find out the voltage induced in the telephone conductor, and that is the voltage that is going to create the radio interference in the telephone conductor. So here this is the configuration. So here we are having P1, P2 and T1, T2. And here P1 and P2 are the power conductors, and T1 and T2 are the telephone lines, because it is symmetrically strung above and below. So it is in the horizontal configuration. The shortest and the longest distances are 2.5 meters and 3 meters. So that means this distance is equal to 2.5 meters and this distance is equal to 3 meters. Okay, so that is about D1 and D2. So P1 and P2 are the power line conductors and T1 and T2 are the telephone lines. Current in the power circuit is equal to 100 amperes. We will have to find out the mutual inductance between the power line and the telephone line. So what is the mutual inductance between the power line and the telephone line? It is equal to 4 into 10 raised to minus 7 ln D2 divided by D1. D2 is equal to 3 and D1 is equal to 2.5. So you can substitute the values, and then the maximum mutual inductance between the power and the transmission line is equal to this. So what is voltage induced? Voltage induced is equal to omega mpt. So what is omega? Omega is equal to 2 pi f. Frequency is given as 50. MPT is equal to 0.73 into 10 raised to minus 7 into the net current that is passing through the line. So what is the current that is passing through the line? The current that is passing through the line is 100 amperes. Okay. So omega mpt into I is the Vt. So what is I? I is equal to 100 amperes. So substituting the value of 100, magnitude Vt will be obtained as 2.29 volt per kilometer. So 2.29 volt per kilometer will be induced on the communication line due to the power line that is running above, carrying a current of 100 amperes. And this induction is happening only purely due to mutual induction between the power line and the telephone line. So this is a very good question. It's an application type of a question. These kind of questions can come in various examinations. So what is the net voltage induced in the telephone line? It is equal to 2.29 volt per kilometer. So what is our answer? Our answer is option C, 2.29 volt per kilometer. So that is about question number 22. Now moving into the next question, which is question number 23. Consider a bundled conductor of an overhead line consisting of 3 identical subconductors which are placed at the corners of an equilateral triangle as shown in the figure. If we neglect the charges on the other phase conductors and ground, and assume that spacing between the subconductors is much larger than their radius, then the maximum electric field intensity is experienced at, whether it is experienced at x, whether it is experienced at z, or whether it is experienced at w is what is the question. So we will read the question once again. Consider a bundle conductor of an overhead line consisting of 3 identical subconductors placed at the corners of an equilateral triangle as shown in the figure. If we neglect the charges on the other phase conductors and ground and assume that spacing between the subconductors is much larger than their radius, then the maximum electric field intensity is experienced at x, w or z is what is the question. So we are going to draw the electric field intensity at various points as shown. So we are having points at x, y, z and w. So 4 points are there. Y is there, x is there, z is there, w is there. So we are going to draw the corresponding diagrams of electric field intensity. If we are considering the point x, E1, E2 and E3 are balanced arrangements, and when you are considering point y, so this is point y, so all the electric field intensities will be acting in the upward direction. When considering point Z, E1 and E2 will be neutralized and E3 will be the net force that will be available. Considering point W, E1 and E2 and E3 are almost balanced. So it is clear from the above diagrams that the minimum cancellation of vectors occurs at point Y, because here there is no vector to cancel that or there is no other vector, there is no vectors which are acting at opposite directions. So here the net force will be affected, here also the net force will be affected, here cancellation of vectors will happen, but here the entire electric field intensity is acting in the upward direction, even though E2 and E3 are acting slightly through the angle. So the net electric field intensity is highest at point Y. Hence the maximum electric field intensity occurs at point Y due to minimum cancellation of electric field intensity vectors. So what is our question? The maximum electric field intensity is experienced at point Y. Option B is our answer. So this is also a question which can form a theory to many other questions that can be asked over many other examinations. So if these 2 points are only given also, then Y will be having the maximum electric field intensity. So the maximum electric field intensity is experienced at point Y, which will give you option B. Moving into question number 24, total reactance and total susceptance of an overhead extra high voltage line operating at EHV line operating at 50 Hertz are given by 0.045 and 1.2 per unit respectively. If the velocity of the wave propagation is 3 into 10 raised to 5 kilometers per second, then the approximate length of the line is what is the question. So the total reactance and total susceptance of a lossless overhead EHV line operating at 50 Hertz are given by 0.045 per unit and 1.2 per unit respectively. If the velocity of wave propagation is 3 into 10 raised to 5 km per second, then the approximate length of the line is to be found out. So we are going to find out the length of the line. So the reactance is given as 0.045, susceptance is given as 1.2. So the net base impedance, which is ZB, can be found out as X equal to 0.045 ZB. Okay, and then what will be Y? Y is equal to 1.2 divided by ZB. So these expressions you have to write it down and you have to put general expressions in the box. Okay. Now assuming L as the impedance of the line, then what is net reactance? It is equal to omega L into L, and the capacitance is equal to Y is equal to omega L into C. From this we will be able to obtain the length of the line. Okay. So L is the length of the line. So what is L? L is equal to X divided by omega L. X divided by omega L. So we can substitute the value, and also C is equal to Y divided by omega L. Okay. So we have obtained two expressions with respect to L is equal to X by omega L and C is equal to Y divided by omega L. Now what is velocity of propagation? Vc is equal to 1 divided by root LC, and the value of Vc is given. Okay. So that means we will be able to substitute the values of L and C with respect to these equations. So this C is equal to 1.2 divided by omega L ZB, and L becomes equal to 0.045 ZB divided by omega L. So when you are substituting this into this expression, then and you will be able to substitute for value of omega as 2 pi f, then L will be the only value that will be remaining. Approximate value of L can be obtained from the solution as about 222 kilometers. So what will be our answer? Our answer will be option C, 222 kilometers for question number 24. Now moving into the next question, question number 25. An extra high voltage transmission line again of length 300 km can be approximated by a lossless line having a propagation constant beta equal to 0.00127 radians per kilometer. Then the percentage ratio of line length to the wavelength. So we will have to find the ratio of line length to the wavelength of the system. So we are going to find out that. So wavelength is equal to lambda and propagation constant is equal to beta. And then what is lambda? Lambda is equal to 2 pi divided by beta. The value of beta is given. So we will be able to obtain the value of lambda. So lambda is obtained as 4947.39 kilometers. And the ratio of line length, the extra high voltage transmission line of length 300 kilometers can be approximated by a lossless line having propagation constant beta. Then the percentage ratio of the line length to the wavelength is to be obtained. So we are going to write it in that fashion as ratio is equal to line length divided by wavelength. Wavelength is given, line length is also given as 300. So what is the ratio? It is about 6.06% that is obtained. So option D will be answer for question number 25. Now moving into the next question, question number 26.